Hi, everybody. Hopefully you are enjoying your nice long weekend. I'm not getting this video out as fast as I was hoping to. I was actually up grading gateway quizzes and grading stuff from other tests or other classes also. So the gateway scores are up, and if you didn't pass, then I have contacted you unless I didn't receive it. And I've contacted a few of those people also. But anyway, today we're going to take a look at the chain rule. This is a big deal idea. This is another gateway topic. We've got a gateway coming up on this very soon because this really kind of stands alone as its own little gateway topic. So I'm going to get right into it. Okay, so the chain rule. The chain rule is going to give us the ability to take derivatives of compositions of functions. On your screen right now, you see a whole bunch of different levels of complexity to these functions. We know how to take the derivative of something cubed, would just be 3 times the something squared. You can take the derivative of 3x squared minus 8x. That's easy. That's just 6x minus 8. You guys showed me on the gateway that you're doing just fine with that. Same thing down here with this second one. Square root of something. You guys know how to take the derivative of a square root. You just say that it's something to the 1/2 power, and then the derivative is 1/2 times that thing to the negative 1/2 power. Problem is, if that thing is more complicated than just x or u or t or whatever the variable is, things get more complicated. So there's nothing here, there's no function on your screen right now that you can't differentiate. It's just that the composition, the things happening at the same time that we don't know how to deal with yet. Composition of functions, reminder of how this works. If I say h is f composed of g, you can write it in this notation, or sometimes you'll see it written as with this little circle in between. This isn't fog of x, this is f composed of g of x. That's just a different notation that says we're taking whatever x is, we're plugging it into the g function first, and then the output of that goes into the f function. So if you don't care about the explanation, go ahead and skip this next slide. The reason that we're going to do what we're going to do today goes like this. Imagine we have this f composed of g, where I'm putting whatever the input is into the g function, and then the output of the g goes into the f. Now, if I put a box around both of these functions at the same time, we don't see that it's two functions. We see whatever goes into the first one, and then it does some stuff, and then whatever the output of the second function is, it looks like that's what's happening. I'm putting in this, looks like a little tiny sphere, and we're getting out this, well, whatever this multi-shaped polyhedron is. But we don't see that in between step. That in between step is happening. Think about it like this. The G function machine speeds up, and that's also speeding up the rate with which stuff is going into this F machine. So what we're going to have is we've got these rates. Remember, a derivative represents a rate of change. So when we say G prime of X, that's how fast the G function machine is working. When I say F prime of X, that's how fast F machine is working. And so what we're looking for is the derivative of F composed of G. Well, the formula that I'm going to give you in just a moment is going to say basically it's how fast the second machine is working in terms of how fast stuff is coming out of the G machine. And we also have to factor in how fast things are going into that first function, the inside function. Now, I've looked all over for something that graphically explains how this works. And sometimes I find something that works kind of for me, but then whenever I've tried to show it to a class, it just gets really cloudy and it looks more complicated than it really is. So at this point, I'm going to say, if you want to do your own research into why we do the chain rule, go ahead. If you find something that really clicks with you, let me know so I can use it in future years. But the rule goes like this. That might be a little bit easier than we need. We've got our function. Our function h is f composed of g. We're putting something into the g function first. The output of that goes into the f function. That's how composition of functions work. Here is my rule. This is the chain rule. It says that the derivative of this composition is the derivative of f evaluated at g, so whatever is coming out of the g function, times the derivative of that g function, times the derivative of the stuff inside. So f composed of g, the derivative of f, the derivative of your outside function, evaluated at whatever your inside function is, times the derivative of that inside function. Um, and we'll see. It looks crazy. It looks complicated. Once we do a few of these, it'll start to be just as easy as things like the product rule are getting for you, for those of you who have been making your way through product rule and showed me how you did that on the gateway quiz. That one's just color coded. We don't need that. If we're using Leibniz notation, it's the same thing. I've got y is a function of u and u is a function of g. So this is f of g of x. But instead of using, I guess, this function notation, we're just using these variables. Basically, it says whatever our big function is in terms of what the inside function is times how fast that inside function is changing in terms of x. This looks scary. This looks awful. Here's honestly how most of you are going to remember chain rule. The derivative of f of stuff is f prime of stuff times the derivative of the stuff. And I know this is high-level mathematical terminology that I'm using, but this is honestly how most of you are going to think of this. The derivative of f of x squared is f prime of x squared times 2x, derivative of the stuff inside. I do want to do some specific examples. I'll do lots of specific examples for you guys before I'm done with this video. But before I move away from my slideshow, I'm going to go with this one. This one was inspired by a class a couple years ago that I used to use the term glop, and they suggested that I use the term slime for reasons that you're going to see. Credit to Ian Harpel for giving me the idea to call it slime instead of glop. If I've got the derivative of sine of slime, you guys know that the derivative of sine of slime is cosine of slime. That's old news. What we are learning now is that the chain rule says that if this stuff inside is anything more complicated than just simply x or some variable, we have to multiply by the derivative of the slime, the derivative of the stuff inside. I'll call it slime prime. Again, very high technological mathematical terms that I'm using here. The derivative of sine of slime is cosine of slime times the derivative of the slime, or slime prime. Well, if I tell you that slime is a function that we know how to differentiate, like 3x squared, well then slime is 3x squared, so our derivative would be cosine of 3x squared, cosine of slime, times slime prime. Well, if the slime is 3x squared, then slime prime is 6x. The derivative of sine of 3x squared is cosine of 3x squared times 6x. All right, we'll try another one that's pretty similar to that. And actually, I should be more careful with my notation. This is my function, y equals, and so our derivative is cosine of slime times slime prime. The derivative is cosine of 3x squared times 6x. Okay, another example with slime before we get to some maybe more typical examples. You guys know the derivative of something squared is that something times 2, 2 times the something. So the derivative of slime squared, again, let's use notation here. If y is slime squared, then y prime is 2 times the slime times the derivative of the slime, slime prime. Again, derivative of something squared, the derivative of slime squared is 2 times the slime times slime prime. So when I tell you, oh, by the way, that slime in this case was sine, Well, we know what the derivative of sine is. So if y is sine squared, then y prime will be 2 times sine times the derivative of sine, which is cosine. All right. Again, the derivative of something squared is 2 times the something times the derivative of the something times the derivative of the function inside. Now, one thing I've always thought about when I get to something like this is that new rules cannot contradict old rules. I want to talk about this. If I say y equals, um, oh, I don't know, let's go with tangent of x. I told you a while ago the derivative of tangent, actually, I didn't just tell you, I showed you where this comes from. The derivative of tangent of x is secant squared of x. And I would understand if you would say, well, wait a minute, what about times the derivative of the stuff inside? Well, if I do the derivative of the stuff inside, if I say that my outside function is tangent, so the derivative of tangent of something is secant squared of the something times the derivative of the something, well, the derivative of x is just 1. And so we've been doing it, I just didn't tell you about it because it wasn't important, it wasn't useful. You would have wondered, why do we keep multiplying by 1 after I take derivatives? Well, it comes from this thing called the chain rule. Okay, I think I'm going to stop this. And let's switch over to this so I can write a little bit more quickly than the usual mouse writing that I need to do. So let's go with this. Let's say we have two functions. F of x is sine of x, and g of x is, let's go with x to the fourth. And you guys know the derivative of both of these. You know the derivative of sine of x is cosine of x. The derivative of g of x is 4x to the third power. So what I would like to take a look at is a couple different functions. Let's say h is sine of x to the fourth. We'll take a look at what the derivative of that will be. And then let's go with m of x, just thinking of different letters that I haven't used yet. Let's let m of x be sine to the fourth of x. So this one says let's raise x to the fourth power and then do sine of that. This one says let's do sine of x and then raise it to the fourth power, which, by the way, reminder of notation, some of you may be a little bit rusty on this. When I say sine to the fourth of x, that's the same thing as sine of x to the fourth power. And I'm looking at my screen, making sure that you're able to see this. Wonder if I zoom in a little bit. Ooh, looks like if I zoom in a little bit, it zooms in a lot. Let me try this. Make it a little bit bigger on your screens. Okay, so the derivative of h prime of x, well, I'm looking at this function. I've got sine of something. I know the derivative of sine of something is cosine of something. But chain rule says if that something is any more complicated than just x, we then have to multiply by the derivative of the something. Again, the derivative of sine of x to the fourth is cosine of x to the fourth times the derivative of x to the fourth, 4x cubed. And then to avoid confusion, I'm just going to rewrite this as 4x cubed cosine of x to the fourth. This isn't a necessary step, but without any parentheses here, you might think that this is all one big thing that I'm taking cosine of. I could avoid confusion by putting parentheses around it like that. Those are not necessary parentheses, but they can help avoid confusion. So there we go. This is the derivative of sine of x to the fourth. Let's take a look at the derivative of sine of x to the fourth power, sine to the fourth of x, which is, again, sine of x to the fourth power. Now, when I look at this, I see I've got something to the fourth power. My outside function, my overall encompassing function is something to the fourth power. And so my derivative, the derivative of something to the fourth power, is 4 times the something to the third power. But the chain rule says if that stuff is more complicated than x, we have to multiply by the derivative of the stuff inside. So once again, the derivative of something to the fourth is 4 times the something to the third times the derivative of the something, and the derivative of sine is cosine. And then I would write this in that form, reverting back to the form that the statement or the question was originally stated. This isn't worth points, but just to let you know that this is a way that I would write this out. In fact, I might even skip that step altogether. All right, let's take a look at a couple more examples. I'm just making up off the top of my head. Let's go with a new set. Let's do something similar. How about f of x is e to the x, and g of x is 5x. Of course, the derivative of e to the x is e to the x. The derivative of 5x is simply 5. So let's take a look at a couple different possibilities. Let's take a look at the derivative of e to the 5x. And then we'll take a look at the derivative of 5 e to the x.
Wow. Is that the back?
So starting with the derivative of e to the 5x, I'm going to say that the derivative of e to the something, my big picture function here is e to the something power, and the derivative of e to the something power is e to the something power times the derivative of the something, in this case the something, the inside function is 5x, so times the derivative of the 5x, which is simply 5. And I would rewrite that as 5 e to the 5x. Not a necessary simplification, but one that I would probably do. And then contrasting that with what I've got going on here, I've got 5 times e to the x. Now this one's kind of interesting because all I have here is a constant times a function that I know how to differentiate. So really I've got, as I take the derivative, well, the derivative of 5 times something is just, well, 5. But then times the derivative of the something, and the derivative of the something is e to the x. So I honestly wouldn't even think about this one that way. I wouldn't think of this as a chain rule problem because all I really have is a constant times a function that we know how to differentiate. So I'm going to talk you through this in 2 different ways. One is chain rule, which again, the derivative of 5 times something is just 5 times the derivative of the something, and the something in this case is e to the x, so the derivative of e to the x is e to the x. But I wouldn't think about it that way. I would think about this as, well, the derivative of a constant times a function is the constant times the derivative of the function. So again, chain rule doesn't contradict rules that we already know, but it wasn't really necessary for that specific example. And then I think I'll finish with this. You'll have plenty of time to practice this. We will look at these also on Thursday when we are back together in class. But I would like to take a look at, let's do a triple-decker chain rule problem. Let's do f of x is, how about x to the 5th? G of x is the square root of x. And FGH of x is, I'm trying to think of a different type of a function. We've got trig functions, exponential functions. The only exponential we have is e to the x. Let's just go with cosine. We haven't done any derivatives of cosine yet today. So these are my 3 functions. And I'm going to compose them like this. My new function is going to look like this. M of x is the square root of cosine of x to the 5th power. So I've got 3 things happening here. I've got a square root, I've got something to the 5th, and I've got cosine of something. So when I do something that's more complicated like this, a triple-decker chain rule, as I like to think of them, first you've got to think about what your outside function is. And in this case, I look at this, I've got this stuff to the 1/2 power, the square root of that stuff. In fact, as I saw on the gateway, many of you are just taking something like this and you're just rewriting it as something to the 1/2 power. And that's great. Go ahead and keep doing that. I would probably do the same for something like this. And so if I want to take the derivative of something to the 1/2 power, I know that my derivative, m prime, will be 1/2 times that stuff to the negative 1/2. Okay, good. I've taken the derivative of something to the 1/2 power. But now chain rule says I've got to multiply by the derivative of the stuff. So now my stuff in this case is cosine of x to the 5th power. So now I'm thinking about, okay, what's the derivative of cosine of x to the 5th power? That's the stuff inside of the function that I just differentiated. Well, the derivative of cosine of something is sine of something. But now my something, my stuff inside x to the 5th is more complicated than x, so we've got to keep going. I haven't got quite to the end of this one yet. I have to multiply by the derivative of the stuff inside. In this case, the stuff inside. Derivative of x to the 5th is 5x to the 4th. So what we have here is the square root of this stuff. And the derivative of the square root of something is 1/2 times the something to the negative 1/2 times the derivative of the something. Well, the derivative of cosine of something is sine of something. And then that something is still more complicated than x. And so the derivative of the something, in this case, the derivative of x to the 5th, is 5x to the 4th. And at that point, the stuff inside is x. And so I'm done. I suppose you could multiply by 1 to be the derivative of x, but you certainly don't have to do that. Okay, there we go. That is how the chain rule works. Certainly take a look at the assignment. You've got the assignment that is due on Thursday. Yes, I'm giving you work to do over the long weekend. Hopefully you've got some time Monday, Tuesday, Wednesday to digest this chain rule thing. Get lots of practice at it. Practice, practice, practice. And don't feel limited just to the problems that I've assigned. Take a look at other problems that show up. There's lots of different contexts and ways that we can use the chain rule. Take a look at this section. Digest this section on your own. This is where this class feels more like a college level math class than usual, when you're actually having to read the textbook and try to figure things out from the textbook. And of course, you can always YouTube different examples, other chain rule. I'm sure there are lots of other teachers who have tried to explain chain rule in a lot of different ways. On Thursday, when I see you guys again, we will be finishing up chain rule and then moving on to something called implicit differentiation, which is just a new twist on the chain rule. So it certainly follows up with the chain rule very nicely. So be ready for that. And then the gateway on the chain rule is going to come up really soon. In fact, I'm not looking at my calendar right now, but if it's not Monday, it's going to be right after that. And it'll be similar to the gateway that you guys just took, where here's a function, take its derivative. Here's a function, take its derivative. Pretty straightforward stuff. But that's enough. This video is long enough as it is. So I'm going to say, certainly ask me questions if you've got them. I will see you on Thursday, but practice, 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 practice. Work on this chain rule stuff, and I will see you later. Bye.